Imagine ecosystems with their own early warning network. Drones, robots, sensors, and AI watching oceans and forests in real time. In this project, we'll explore how trusted data and autonomous guardians can detect damage, verify change, and support restoration. We've moved from digital intelligence foundations into swarms that act in the physical world. Now that same logic scales to ecosystems. Forests, oceans, and habitats monitored, protected, and restored by coordinated autonomous guardians. Guardian networks can function like an immune system for ecosystems. Sensors across ocean, forest, air, and space act like nerves, noticing early signs of harm. Illegal fishing, bleaching, deforestation, poaching, pollution, or wildfire risk. AI agents connect those signals, separate noise from real threats, and decide what needs attention first. When evidence is strong, robotic assets can move closer to inspect, document, or support response teams. The goal is not just monitoring. It is a trusted protection layer that can detect, verify, respond, and help ecosystems recover. The Guardian network is not looking for one kind of damage. It has to recognize different threat families in different habitats using different evidence. In oceans, some signals are direct, like illegal fishing or dumping. Others are more subtle, like acoustic disturbance, microplastics, bleaching, or dead zones. In forests, the clues may be canopy loss, road expansion, disease, drought stress, poaching patterns, or the first heat signatures of fire. Across both environments, biodiversity is the deeper scorecard. Species decline, migration disruption, nesting failure, and food chain imbalance show whether the system is protecting life, not just detecting incidents. One way to understand the Guardian network is as a stack that turns environmental reality into accountable action. At the base, sensors and robots collect signals from water, air, soil, soundscapes, and satellites. Above that, AI converts raw data into meaning: species presence, stress patterns, anomalies, and likely future trajectories. The coordination layer decides what happens next: dispatching drones, underwater vehicles, restoration crews, or human reviewers when confidence is low. Finally, the trust layer records evidence and outcomes in tamper-resistant systems, so monitoring, credits, compliance, and public reporting can be verified rather than simply claimed. The autonomous platform layer is the body of the Guardian system. It is how intelligence reaches places people cannot constantly patrol. Aerial drones provide rapid coverage over forests, coastlines, roads, fires, vessels, and animal movement. Marine robots and surface vessels extend that reach underwater, checking reefs, fishing gear, water quality, and habitat change. Fixed edge nodes do the opposite job. They stay in place, listening, and watching over long periods. The design principle is balance. Mobile robots investigate uncertainty. Persistent sensors build ecological memory. Together, they turn scattered observations into continuous situational awareness. Ecological damage often hides in signals we do not immediately see, so Guardian networks need more than cameras. Vision can spot canopy loss, smoke, vessel patterns, coral bleaching, or animal movement. Bioacoustics adds another layer: whale songs, bird calls, insect activity, chainsaws, engines, gunshots, or the sudden absence of normal sound. Environmental sensors capture chemistry and conditions, including temperature, salinity, oxygen, turbidity, pH, soil moisture, and toxins. The real power comes from fusion. AI compares these streams together, separating normal seasonal change from stress patterns that suggest illegal activity, pollution, disease, or ecosystem collapse. Recognition is only the first layer. AI can classify organisms from camera traps, drones, satellite imagery, underwater video, and acoustic sensors. The next layer asks what those organisms are doing: migration shifts, feeding disruptions, breeding failures, or predator-prey imbalances. Temporal models then compare today's signals with baselines, seasons, and expected climate conditions. That turns scattered observations into ecological intelligence. A missing pollinator, a quieter reef, or a sudden invasive species spike becomes evidence about system health, not just another data point. An environmental digital twin is a working model of a real ecosystem. It blends sensor feeds, drone imagery, field surveys, climate data, and human activity into one changing picture. From there, AI can test futures before they happen. Coral bleaching, fish decline, fire spread, illegal logging, or reforestation recovery. The value is practical. Instead of guessing where to send crews or funding, conservation teams can compare interventions in simulation first. Over time, the twin also becomes a memory of change, showing whether an ecosystem is degrading, stabilizing, or becoming more resilient. DLT becomes useful when ecological evidence needs to be trusted across many parties. A field photo, sensor reading, acoustic file, or species observation can be recorded with its timestamp, location, device identity, data hash, model version, confidence score, and validator signature. The ledger does not have to store everything. It stores proofs that make later tampering visible. That matters for enforcement, conservation credits, treaty reporting, insurance triggers, and court evidence. The key governance trade-off is transparency without exposing sensitive habitats or endangered species locations to new risks. The Guardian network works as a closed loop, not a one-time alarm. Sensors gather many kinds of evidence: imagery, sound, chemistry, satellite data, and movement patterns. I looks for signals that do not fit the expected baseline, such as night vessel activity or sudden forest loss. High-priority alerts are then investigated by drones, boats, or field teams, adding closer evidence. That evidence is verified before anyone acts. Finally, trusted information reaches the right people, so restoration, enforcement, or community response can happen quickly and with confidence. Swarm coordination shifts conservation from one machine following one route to many agents adapting together. In forests, drones can split patrol areas by fire risk, terrain, season, and past poaching patterns, then reassign coverage when a threat appears. In marine systems, robots can share reef findings, track vessels, and map biodiversity corridors without repeating the same inspection. Edge AI lets each agent make safe local choices when networks are weak, while cloud or satellite links synchronize the larger mission. The key constraint is ecological safety. Coordination must protect habitats, not overwhelm them. Restoration intelligence is where Guardian networks become more than alarms. In a damaged forest, detections can point teams toward replanting zones, invasive removal, fire breaks, soil repair, and watershed protection. In a coastal reef, the same loop can guide coral planting, seagrass mapping, ghost net removal, and nursery recovery. The AI does not choose only what is urgent. It weighs feasibility, cost, community needs, and likely regeneration impact. Then monitoring continues, measuring canopy return, coral cover, species recovery, and reduced illegal activity, so each action improves the next one. By 2050, machine-assisted guardianship could turn conservation from occasional inspection into continuous protection. Satellites, drones, sensors, and field teams create a live evidence stream across oceans and forests. AI looks for anomalies: illegal fishing, logging, pollution, habitat stress, or failed restoration. When risk rises, alerts move quickly to communities, scientists, and regulators, with records that can be trusted and acted on. The bigger shift is precision. Restoration teams learn where to intervene, when to adapt, and whether nature is actually recovering. The goal is not replacing stewardship, but scaling it. Ocean and forest guardian networks show autonomy as stewardship, not just efficiency. Robots, sensors, ecological AI, digital twins, and trusted records create a closed loop: sense, analyze, verify, inform, and restore. That same swarm logic now extends outward to space construction and mining, then inward to urban mobility. Autonomous systems can extract and build, but founders choose what future they encode.